Okay, so this is a book called Bomb. It is nonfiction, and it says it's the race to build and steal the world's most dangerous weapon. So what do you suppose or what do you predict this is about? What bomb? The nuclear bomb, correct. And it was written for students, so it's not going to be super technical in its terminology or its science explanations, but we do want to look at it, okay? Now, I've skipped chapter 1. We're going to go right into chapter 2. It's called the U business. See? And I know that this is going to be explaining the science. It's page 13, technically. And discovery behind that nuclear bomb, like Julian said. Now, again, we are working on AKS 13. And here I'm going to think about how the author uses and refines. That's a big word. What does that word refine mean? Anybody know? Kind of, Deja, what are you thinking? So redefine, so continuously redefine, continuously refine what it is that the word means so that we get a better understanding of it, or refining key ideas. So sometimes that looks like explaining them in different ways or over and over again. So it can be words or it can be key terms or ideas over the course of a text. Now this is my controlling question or my essential question that I need to think about as I read. All right, let's just begin. Actually, theoretical physicists were about to become more powerful than Oppenheimer had ever imagined. In late December 1938, in the German capital of Berlin, a chemist named Otto Hahn set up a new experiment in his lab. By the late 1930s, scientists like Hahn understood that everything in the universe is made up of incredibly tiny particles called atoms. Now, I know an atom because my daughter had to make a plant cell with a cake recently. Did y'all do that in middle school? And you had to like put the candy was the nucleus, and then you had to put like, I don't know, gummy bears for the chloroplasts, and or some kind of model of a plant cell. So my mind is triggered. I know what an atom is. So let's see how he refines this. He says they knew that atoms themselves are composed of even smaller particles because atoms have a central core, or a nucleus, made up of protons and neutrons packed tightly together. Surrounding the nucleus are electrons. So immediately he's now giving us sort of a background information on atoms. He's defining them quickly, defining their composition of them quickly for readers as like a brush up. You know, like to have background knowledge. You know, like how bombs explode, like when they jump in, like when they run as a cover, like the atoms separate, well, let's keep reading because I think they're going to explain this to us. So scientists also knew that some atoms are radioactive. Here's another word that's coming about, okay? That is, their nucleus is naturally unstable. Particles break away from the nucleus and shoot out at high speeds. And this was useful to experimenters like Hahn because they could use radioactive elements as tiny cannons. So he's taken the word radioactive, he's explained it, but then he's used a figurative language, right, called tiny cannons. I like it. Tiny cannons to help me visualize what it is that radioactive means. And so basically radioactive atoms are like tiny cannons. Yes, Kevin? Not yet, but when this is over, you may. All right, keep going. Hahn began his experiment with a piece of silver-colored metal called uranium. Here's a new key term. He placed the uranium beside a radioactive element, and he knew that neutrons would speed out of the radioactive material. He knew that some of these tiny particles would hit uranium atoms. Okay, so a uranium is an atom. Do y'all know other atoms from chemistry? If uranium is an atom, what's another atom? You're thinking in the right direction. You're thinking in the right direction. What are those things made up of? Oxygen is an atom. Carbon, helium, hydrogen, right? So we're talking about the elements. So uranium is one of them. So now that I understand that uranium is an atom, I'm starting to understand the concepts that he's pulling together. He said the big question was, what happens when a speeding neutron crashes into a uranium atom? Interesting. The answer was shocking. Han was sure he'd made a mistake. As expected, some of the speeding neutrons hit uranium atoms. What staggered Han was that the force of the collision seemed to be causing the uranium atoms to split into two. And according to everything that scientists knew in 1938, this was impossible. So he's setting this up as impossible, which creates a curiosity for the reader. It makes me excited to see what happens. At once, excited and disturbed, Han needed help, so he turned to his former partner, Lise Meitner, who was a woman, a Jewish physicist, who had been forced out of Germany by Hitler. Of course, she's a woman. She knows the answers. Anyways, that's a joke. Han wrote to Meitner at her new office in Sweden, describing the strange results of his experiment. Perhaps you can suggest some fantastic explanation, Han said, of the splitting uranium. We understand that it really doesn't break up, or it really can't break up. Meitner responded immediately, agreeing that the news was amazing, but adding, we have experienced so many surprises in nuclear physics that one cannot say, without hesitation, about anything, that it's impossible. A few days later, Meitner's nephew, Otto Frisch, also a physicist, came to Sweden for a visit. Over breakfast, she showed him Han's letter. I don't believe it, he said. There's some mistake. The two went outside to discuss the mystery. We walked up and down the snow, I on skis and she on foot, and Frisch recalled. They talked over an idea proposed by the great Danish physicist Niels Bohr. Bohr had recently suggested that the nucleus of an atom might act like a wobbly droplet. So we've got this concept of a splitting atom, a splitting uranium atom. And now he's refining this by calling it a wobbly droplet, like water, like liquid. If that were true, they asked each other, what would happen if speeding neutrons hit the nucleus of a uranium atom? Could the force of the collision cause the uranium nucleus to stretch and stretch just like a liquid drop until it split? So we've got sort of like this analogy that he's creating to help us understand what it is that a uranium atom will do when a neutron hits it. They brushed the snow off of a fallen log and sat. Meitner pulled out a scrap of paper and pencil, and Frisch sketched a diagram of a circle stretching into a long oval shape and finally breaking in two. Do you see this diagram down here? So here's the uranium atom. Here's what happened when the neutron hits it. It starts to pull apart. It reminds me of those squishy things that you can get out of the vending machines. And then finally, it separates. So not only has he given us an analogy of the wobbly droplet of liquid, right? He's also giving us a diagram. These things equal visuals for the reader. This is how he's refining the concept of nuclear atoms like uranium splitting. All right, that's an illustration for us. Let's keep going. We only have a little bit more that I'm going to go with, okay? And then we're going to move on. Yes, said Meitner, that is what I mean. They agreed. This must be what happens to the uranium atoms in Han's lab. Meitner took the pencil and paper and began working the math. If you really do form two such fragments, she said, they will be pushed apart with great energy. And atom splitting was incredible enough because I didn't think that could happen, right? But what made this a world-changing discovery? So now I understand that it's not just a matter of the uranium atom splitting, but somehow this is super important. That this is, if atoms really could be split, they would release energy as they broke into two. But how much energy? Just enough, Mettner and Frisch calculated, to make a grain of sand jump. Okay, that doesn't seem like a lot to me. A grain of sand jump. Well, that's not that big of a deal. But that doesn't sound like much. Keep in mind how tiny atoms are. So with 238 protons and neutrons, uranium is the largest atom in nature. He's continuing to refine what uranium is, and no wonder the nuclear bomb, uranium is a part of it, right? I didn't realize that uranium was the biggest one when it comes to protons and neutrons. I would have guessed something like hydrogen or oxygen, but apparently that's why uranium is so important. So then he says, with 238 protons and neutrons, uranium is the largest atom in nature. Still, each atom is incredibly small. A single ounce of uranium has about, can anybody read, what is that number? What is this number? A quintillion? I don't even know. 100 trillion? That's not even a trillion. I don't know either. But here's what I do know. Let's pretend that this was quadrillion, okay? Let's just pretend. Look how I wrote quadrillion. Does writing out quadrillion have the same effect as writing this out like this? Why do you suppose he chose to do it this way? It creates that visual impact of extreme largeness, right? So you wanted it to look like that. So that was a choice move on the author. All right, last bit. So what if you had a 20-pound lump of uranium, a 50-pound lump? What if you were able to get all of those atoms to split and release energy at the same moment? You would be having by far the most powerful bomb ever built. And we know that's exactly what they did with this information. And I'm just going to add this last part, which I thought was really important, about how it made him feel when he created it. He said, I felt as if I had caught an elephant by its tail without meaning to, and now I don't know what to do with it. So it's almost like he was reaching for just a tail, and then what was attached to it was more than he had ever bargained for, and he didn't know what to do at that point. But the whole purpose of this lesson was that I wanted you to see how I might go through and look at how an author takes key terms like uranium and atoms, right, and radioactive, and refines them so that we get a better meaning and there's a better impact. And so I have said that the author is effective in establishing the scientific process of the nuclear bomb's inner workings by using analogies such as wobbly liquid and drawing diagrams to help the reader visualize what an atom undergoes during a reaction that we know to be called the nuclear bomb. And guess what? It's your turn to do the same kind of work with a different text. So that's what's going to happen.